All right. So I do advise that you can practice this by try to participate in today's activity because it will be more of trying to figure things out rather than discussing the concepts. Of course, we will connect it to the concept of GA, but more importantly, how to solve problems using GA. So I've also uploaded 3 more links or file, one file and 2 YouTube videos at the optimization part um, of Canvas. Let me share my screen. We'll sort of watch these videos in a while para makita natin kung ano yung intuition behind GA. But before that, let's just do a short review. Okay. All right. Okay, so these are the 3 files. I have a reference paper for the different crossover types, and then just rename this. These are GA visual examples. Okay, that you can watch later on. Okay. All right. So again, what does the GA algorithm solve? It essentially solves the optimization problems where we are either minimizing or maximizing something. Now, to minimize something, we need what's called a fitness function. Minimize or maximize something, we need a fitness function. The fitness function that we discussed last time, wherein we tried to solve the problem of determining what a good or what a bad politician is, no? Is given by multiple solutions, and the algorithm essentially iterates through every generation, evolving random solutions until it comes closer to the fitness function. And we said that the fitness function for this is the minimum value, simply adding all the values of a particular solution, and we want it to be as low as possible. We've also seen in the example ng code, no, na it will depend on the parameters that you put in. For example, a very low generation value might sometimes yield a suboptimal solution, yung may 1 pa doon sa string bit natin, sa bit string natin. But it's good enough. Right? And if we increase the generation, eventually we'll come up with an ideal solution. Okay? And that's the idea of GA. Okay? So, let's talk about a classical problem. No? So, sorry. Before that, the solution is simply an array that represents a possible answer to your problem. Okay. In the case of the bad politician, we want everything in our array to be 0. When we sum the values inside our array, we want it to be 0. That's why our fitness function, if we take a look at our code, it will look something like this. Right? We simply return the sum of all the items in our solution. Okay. So before I go to another problem, may questions ba or may clarifications ba about GA? Some of you can actually use this as projects. No? Some of you are already in step 2 wherein you're trying to solve for the algorithm itself. You're trying to optimize something. Although they can be solvable by the other algorithms that we discussed, GA is another option for it, to look for an optimal solution for your problems. And it's essentially a search. It's a form of search in a way, wherein you provide stochasticness or randomness in your solution that will eventually reach an optimal solution. Right. We also have the different steps of the GA algorithm. We start with a fixed population. And then from that population, we select the best individuals, which again is based on the fitness function. Right? Best individuals should have a score that is close to the fitness function as we want. So for this particular session, let's focus on that because everything else is essentially formulatic. Meaning to say that it has an exact process, and the real trick is to look for a good fitness function that fits your problem. Okay, so let's try to see if we understand this. And the classical problem for GA application is the knapsack problem. Now, the knapsack problem is simply an optimization problem wherein you have a knapsack or a bag, essentially. Ito yung drawing ng bag. Okay. May something dito. No? And then you can, that bag has a constraint. So let's say 5 kilograms. Okay. Now, in the 5 kilograms, you probably encountered this problem before. No? The idea there is how many objects can I fit? The most number of objects I can fit into the bag, okay, without exceeding 5 kilograms. So I might have, let's say, a star, which is 1 kilogram. Okay, I might have, let's say, a ball, which is 3 kilograms. Okay, and I might have other objects, a circle, which is 2 kilograms, or a square, which is 4 kilograms. Okay. Now, I want to fit the most number of objects inside this bag. So how do we frame this in terms of a GA problem? Again, we look first for a solution, or we represent a solution in the form of an array. Now, in this particular case, even if we don't try to sort of programmatically solve this problem, okay, we can just check. All right, we can eyeball it, so to speak. Okay, so in the bag, I could fit, let's say, a star and a ball. Right? So one possibility is okay, we get a star, we get the ball. If we add the two values together, that's 4. Okay, we're still within the bounds of 5 kilograms. However, we cannot add another object. Right? We cannot add any more a circle. Okay, medyo bad example. Ano kaya pwede to? An apple. Parang hindi siya mukhang basket. Okay. An apple to the bag kasi 4 plus 2 is already equal to 6. So you can't exceed the 5 kilogram value. No? Similarly, you can't add this box inside the bag because you already have 1 plus 3, 4 plus 4 is equal to 8. 8 is more than 5 kilograms. So one solution is to have a star in a ball. Similarly, I could also have an apple and a star, okay, which is equal to 3 kilograms. Okay, but the question is, am I optimal? Because those are two items. It still fits our constraint of 5 kilograms. Okay, but how do we say it's actually better than a star in a ball? Okay? Or we could actually have a square or a box, if you will. No? A box, right? And a star, because 1 plus 4 is equal to 5. So it's still within our bag. So that's what we refer to as the knapsack problem. How many objects can we fit in a bag based on its weight given a certain constraint? Now, how do we set this up in terms of the GA problem? So in the GA problem, we want an array. And in this case, we can actually represent a solution by the presence or non-presence of that object. So for example, we can have a star and we can have a ball, but we can't have, if we have a star in a ball, we can't have an apple in a box together with it. Okay, so one solution is star, ball, not apple, not box. Okay. Another solution would be, we could have a star, so we have a 1. For the ball, okay, let's say we don't decide to use a ball. Okay, so 0 si ball, 1 si apple. Can we fit square, box? Hindi na. So 0 to. Okay. But the way, this is still eyeballing it because we are manually looking for possible combinations of these objects to fit inside the bag. Okay. So the GA allows us to create a more structured way, although it's based on randomness, to fit stuff inside our bag, okay, and represent each solution as having this object or not having this object with a specific weight. Okay? So even before going to the initialization of population, because initialization of population, that's simple. We define a number, let's say 500. Okay? For each of those 500 counts, each count will represent a solution. So in the case of our example, each count will represent what we again refer to as a chromosome, which is now, according to this drawing here, is an array of length 4 of either ones or zeros. So again, we refer to this as a chromosome. And then each element in that chromosome is what we refer to as a gene. Okay? So if we define 100, we essentially have 100 chromosomes of different combinations of ones and zeros, randomized. You can have a distribution for it, but it's essentially a random solutions. Okay, that's the first step of GA. But again, before we get to that part, we need to understand the problem at hand. Okay, so in this case, if we frame the problem this way, who can tell me if this is a minimization problem or a maximization problem? And why do you think it is minimum? It is trying to minimize something or maximize something. What do you want to actually achieve in this case? What is ideal for you? Ayun na lang. What is ideal for you? How would you answer that question? Doesn't have to be programmatically, no? Pero in terms of framing the problem, what is ideal for you in this situation? Anyone? What do we want to achieve?
Is it trying to fit the most number of items, sir?
Okay, you could say that. What's ideal for you is that I want the maximum number of items that can fit inside the bag. So in this case, what is it because of what you said? Is it a minimization problem or is it a maximization problem?
Maximization, sir.
Minimization? Why do you say it's
Maximization, sir.
Maximization? Yeah. So it's a maximization problem wherein your ideal situation is still the same. It's the max. It's actually the opposite of the problem we discussed in the slides. How many items? So if you add everything here, it has to be the maximum possible value. Okay. So therefore, your fitness function will still be the same as the fitness function in our GA example. Right? You sum everything together. It's such a because your representation is not the weights. Your representation is the presence or non-presence of the object, right? Wherein if you bundle everything together, you want the most objects to fit in the bag constrained against your value of 5 kilograms. Okay? So in a way, your fitness function, okay, is still the sum of all the elements in it. Right? Wherein you return a score. But what is missing here? Ayan. It's not simply the sum, but what else? If we're talking about that knapsack problem, if you were to create a fitness function, because we could have a solution, no? We could have a solution na, kasi random to, na 1, 1, 1, 1. Right? If we do this, remember the fitness function returns a score. So if we add everything together, the answer is 4. So it's definitely better than star and a ball, because star and a ball is equal to 4, is equal to 2 rather, 2 objects, right? But it's still within the constraint. So it's not as simple as a sum, but what else is missing here in terms of developing your fitness function? Who can suggest a variation of this fitness function? Kahit logically, doesn't have to be the code itself.
Question, sir. Yung
Yes.
sa fitness function, is it the function itself na nag-filter out na, or it's just the function that evaluates the parang score of a certain chromosome?
Okay, so if you take a look at the signature of it, no, part of part of the parameter of the function is the solution, which is our chromosome. No? So at the very least, the input of the function is the solution. And eventually, in order for us to perform selection, we need all our solutions plus its corresponding score. So the fitness function is the score, should return the score of a certain solution.
So it's like as a function that evaluates the score of
The
a certain.
score. Yes. Yep. Now my question was, a possible solution, given that framework, no, a possible solution is everything is one. Okay, but in our particular problem, that's why optimization problems are tricky, because there is a chance na magkakaroon ka ng some sort of constraint to the problem. Okay? So, what do you think can we modify in the fitness function so that it returns a score depending on the solution that you passed with? So in other words, hindi lang pwede basta sum. Kasi if we did basta lang sum, then this one would be a correct solution. But then, it will not fit our constraint. Okay, so logically speaking, what can we add to this? Sorry, Austin, you were saying some dun sa chat. What do you mean by maximization problem given a threshold?
Sir, like we want to maximize the amount of items we can put given a specific ceiling.
Yes, given a specific ceiling value, right? Wherein each chromosome is represented by bit strings of ones and zeros. Yeah, correct. So, yun. So sa case natin, how do we modify our fitness function for it to be properly framed as the fitness function that we need?
We multiply the ones with the weight of each item.
Okay, so if we multiply the ones with the weights of each item, so what you're saying is 1 times 1, 1 times 3, 1 times 2, and 1 times 4. Now, what will be the score if, let's say, we input this chromosome? What should be the score?
10, sir.
10? Okay, so if it's 10, and we are trying to maximize, because we already defined that it's a maximization problem, will that work for this particular problem? Because if we say a score of 10, then by evolution, this will be the ideal chromosome. So in other words, hindi siya pwede 10. Right? So we need to modify the fitness function. We need to do something with the fitness function so that it also gives a score that is not ideal if it does not meet the constraints of the problem. So how can we modify that in this particular example? But good try. You multiply the weights to wherein our weights are literally the weight of the item. No? Kung 1 kilogram siya, 3 kilogram, 2 kilogram, or 4 kilograms. But what else do we have to do? Remember, we're maximizing it. Anyone? I think I can draw here. Para hindi ako switch ng switch. So we have our bag. Our constraint is 5 kilograms. Right. We have a star. We have a ball, an apple, and a box. 1, 2, 1, 3 pala. 1, 3, 2, 4. These are the weights. 1 kg, 3, 4, 3, 2, 4. 3 kg. Short-term memory loss now. 2 kg. Yeah. Okay, anyone? Okay, so that was a good try. Again, the problem we're trying to solve is what if we had a solution in our population that looked like 1, 1, 1, 1. Okay. Essentially, do we want this as part of the solution? It is the maximum, yes. But do we want this as part of the solution? Yes or no?
No.
No. Okay, it's not part of the evolution. We should not let it breed, essentially, no? Kill it with fire and everything. So, no. So therefore, logically speaking, we want this score to be 0. We don't want to maximize this score if we had a solution this way. Okay, so theoretically, if we feed this solution to the fitness function, the score should be 0. Because we don't want that to be part of the solution. That type of configuration of that solution should be 0. So what is the constraint that we have to add to our fitness function?
If it's greater than 5, sir, then
Okay, so we could develop some sort of custom fitness function that when computed should return a low value. Okay? Or 0 for short. No? So you can do this different ways, no? But let's say custom, or let's call this the knapsack fitness function. Right? What else do we have to pass here? Well, we have to pass the solution. We also have to pass some constraint. Okay, and then we also have to pass the maybe some config. Right? Parang the idea there is the config will be this part. Right? The weights. So that given some solution, we can multiply it to the config, or para lang mas readable, we can say weights. Weights tapos yung constraint natin. Okay, we're in the default of the constraint is, let's say, 5. Okay. So what we could probably do is, if the solution, so we might have something like for each element S inside the solution, we want to get sort of the sum of it all. Sum. Okay, parang sum plus equals the solution, which is either a 1 or the gene. Okay, gene. Okay, plus equals gene times the weights at that particular index. So let's just use an index na lang. For index in range solution, range of the length of the solution. Yan. Now, so we want to like an index for each. So we know where we're looping. The solution at sub-index I, right, at some index, multiplied by the weights at that index will give us the sum. Now, what can we do with it? If the sum is greater than the constraint, okay, ayaw natin yun. So the fitness function of that solution will be 0. Right? Else, we can return the sum of the solution, because we want to maximize like what is the best solution that will give us the most objects, right, inside that particular bag. Okay. Right. And this is what we need to know how to develop. Okay. What is a good fitness function that matches our problem? Okay. Sige. Questions muna dito sa idea na to of a custom fitness function that we try to frame for our problem. Questions? Clarifications? Okay. So let's practice that. Yun yung point ng sync session yun. So that when we take a look at other problems, we sort of have an idea on how to solve it. Okay, let me know if there are questions. No? The thing is, with this type of algorithm, unlike the others that we have discussed so far, there parang wala siyang closed form. It is very subjective to the type of problem you are trying to solve. Okay? So let me just refresh this. Okay, let's talk about another problem. And let's see if we can identify both yung itsura ng solution, how the solution looks like, and what our fitness function is. Okay, so let's say pathfinding. Let's say we are a rat in a maze, no? Or rather, uh, you're a rat. How do we draw a rat? Lack of drawing skills. You're some entity. Okay, that's in a maze with a bunch of may mga harang. No? See, this is a harang. This is ito harang din to. Okay, and then let's say you have like other obstacles in the maze, something like that. And you want to reach the cheese. Cheese is found somewhere here. Okay. So let's give some parameters to the problem. Let's say that you want to reach the cheese in 5 moves. Okay, so in other words, a potential solution would be move here, 1, move here, 2, 3, 4, 5. Okay. As a rat, I want to reach the cheese in a matter of 5 steps. Okay, so think about the problem first, and then try to come up with a solution. And how do you think you would represent a chromosome that is the solution to the problem? Okay, let's assume 2D space. So you have an x coordinate and a y coordinate. Okay. So how do you think you would represent a solution if the only details that are given is I want to reach the cheese in a matter of 5 steps? I'll give you some time to think about it.
Clarification, sir. Won't this be more fitting sa like the graph?
Yes. Yeah. You can actually model it in a graph, but if you model it in a graph, ang dami mong mga possible, if you were to model this in a graph in an XY 2D plane, ang dami mong nodes, right? And then let's say, kung clear naman yung mga squares dito na sa whiteboard. Like each distance, to keep it simple, each distance between the squares might have a distance of 1. So something like 1 edge, 1 edge, 1 edge, something like that. Right? Pero ang dami niyan. No? And again, we want the GA to sort of be an easier way to solve this problem by using randomness. So ibig sabihin, if I declare a population, if we can figure out the solution and we declare a population of 1,000, eventually, just by using those 1,000 data points, we can eventually get to the cheese. Okay. So yes, it is better to model this as a graph. But what other possible structure can we? Because if we model this as a graph, we also have to exhaustively draw out all the possible like coordinates that is also constrained with 5 steps to get to the cheese. Yeah. So it's a rather difficult problem kung graph siya.
Thank you for clarification, sir.
Let's try to give you a hint. Meron tayong, if it were 5 steps, then it means that from the point of origin of the rat, it would go from however you might want to represent this, no? To this point, and then another line to step number 2. Kunwari na lang, tinlagpasan niya yung obstacle na yun. To this point, this point, this point, and then finally cheese. So usually in these types of problems, again, we won't solve the entire problem. No? We want representation first. How do I represent the solution to this problem as an array? Kasi ang chromosome ay array, right? Of things to get to the cheese. Now, to guide you out, since we're in an XY plane, we can assume that the first step will be a coordinate. So some XY coordinate. This one would also be an XY coordinate. This one, an XY coordinate as well. And this one would be an XY coordinate. Also this one. And we know, sorry, I forgot to mention one thing. We know the coordinate of the cheese. So the cheese, let's just call this, is in coordinate x prime, y prime. Okay. Now, to ease you in on this problem, let's first answer the question, is this a minimization problem or is this a maximization problem? Because we know that it's an optimization problem. We want to find the optimal path from point A to point B, given a Cartesian plane, xy coordinates. So how do we know that logically speaking, how do we know that the path is optimal from one point to another? And anyone care to answer that question?
Distance formula.
Okay, pwede, yeah, exactly. Distance formula. Now, given the distance formula, is it a minimization? Again, the question is it a minimization problem or is it a maximization problem?
Minimization.
Minimization. You want to minimize the distance from point A, the rat, to point B, the cheese. Okay, so you have a clue. Minimization. Okay, so we have that settled. Minimization problem. Kleb, you're saying something. You're about to say something yata.
Wala, sir. I was
Okay.
trying to write it up lang.
Sige. Yeah. So one technique here is to use a pen and a paper, so you can sort of visualize what you want. So tama, you want the minimization problem, and then the objects will actually be your constraints, right? Now that we want it to be a minimization problem, how do we represent the path? Remember, a solution is represented as an array of values. And we know the endpoint. We also know the starting point. So this is something like some x hat, y hat. So who can give me a representation of this solution? Okay, yun na yung hint. We can use the distance formula. So the distance formula is any equation that you can Google up that gives you the geometric distance between point A to point B. Okay, we want to minimize that. Okay, of course, we have constraints, which are the obstacles. But before we think about the constraints, we need to think about other things. Now, we want to create a 5-step path to the cheese. Or tama ba? 6 steps ba to if you include the cheese? Okay, but in any case, we want to represent that path. Okay, so what will the array look like? So that, also think about one more thing. No? So that if we fit that array, or if we feed that array to a fitness function, we can try to come up with some sort of like equation that will allow to give us a number that we hope to minimize. Okay. Now, maybe for some of you, it might be easier in code just to sort of try to visualize it. Let's say we have another function here called the rat maze fitness function. Okay. Of course, we need the solution. Okay. We don't know what that looks like yet. And then what are the other givens? We said that we know the endpoint. Okay. We also know the starting point. Okay. So start point, and endpoint. Although come to think of it, I don't think we need the start point. We can pass the start point. Probably like represent it as kunwari lang, no? 0, 0, and then the endpoint will be some coordinate sa plane. Maybe 40, 25. Yan. So given that, what do you think does the solution look like? And what do we already know? We want to minimize the distance between point A and point B. So let's try to come up with a score. If this were a minimization problem, okay, and let's just come up with a distance metric. You could search sa Google like what is a good distance metric. Usually ang lalabas dyan would be something like the Euclidean distance. No? So distance metric formula kunwari. Ayan, meron from the get-go. 4 types of distance metrics in machine learning. So malamang yung isa dyan Euclidean, of course. Yan, Euclidean distance, you have the Manhattan distance. Some of you are is doing a distance problem for the project, diba? Yung Levenstein distance. Right? So that's an example of a distance metric. Although it's not, I'm not sure if you can make it a geometric distance, no? Pero it could probably be used as a distance metric from point A to point B. Okay? So marami ng formulas dyan. Let's just invent our own. Let's just say that it is the absolute value of the start point at index 1 minus the end point at index 1 as well, the first index, plus the absolute value of start point at the second index minus the end point at the second index. It could be as simple as this. Distance. And why do we want this? Because again, the purpose of an objective function is to return a score given some solution from start point to end point, at least in terms of the rat maze problem. Okay? But what we are not considering here in the distance will be the solution. Okay? And the hint is the solution should be a 5-step coordinate to cheese. In 5 steps, I need to reach the cheese. Okay, so one possible solution is the array of coordinates until the what do you call this? Until the endpoint, right? So your actual distance is sige, let's use para lang correct tayo mathematically. No? Let's use an actual distance metric. So the easiest would be Euclidean distance, which is each element of P and Q, where P and Q are arrays, you simply subtract it and square it. So it will always be a positive number. Okay? So how do we implement that? So let's start with distance is equal to 0. No need to include start point. Kasi we know that, well, sige, we could include the start point. So the first distance metric will be the Euclidean distance between start point and the distance between the first element of the solution. Right? So distance is equal to distance plus the square root of, do we need math for this? Import math or something. Those are just technicalities now. So let's just say we know how to square root something. Okay, square root of coordinate 1 ng solution. So the first element at coordinate 1. Okay, so the suggestion in chat was if we draw it up, it would be something like an array. Solution would be an array of xy coordinates. x1, y1, okay, x2, y2, x3, because we need 5, no, 5 hops to the cheese. x3, y3, x4, y4, and then finally x5, y5. Right? So if we frame it this way, then the score of a certain solution will be the distance between the starting point, whatever that starting point is, okay, between the first element of the solution. So start point at this value, okay, minus, okay, plus square, mali. Need to square this. Something like this, right? Plus start point at the second element, no start point, minus solution 0, 0. You need to square this as well. Okay, and then we square root it. Okay, so it's like saying, going back to the drawing board. Okay, it's like saying we're getting the distance from this one to this one. Okay, makes sense? Okay, so that's this part. And then we can simply iterate through each pairs of coordinates. No? In fact, you can manually do this, right? So start point, instead of start point, you now have solution. The first coordinate of the solution to the first coordinate of the next step of the solution. Okay, same goes for this one. Solution 0, 0. Or rather 0, 1, kasi second element ng first, second coordinate ng first element ng solution minus yung second coordinate ng second element ng solution. 1, 2, 3, 4, 5. Okay. And then the rest is just an iteration. Of course, you can do a loop. This para lang broken down talaga yung solutions natin. So this one will now be 1, 2, 3, 4. And we sort of move the window to something like 2, 3. Actually, hanggang dito lang. Okay. Oh, the last one would be the cheese. Right? Tama ba yung ginagawa ko? Yeah. Right. So this one would be 1, 2, 3. This one would be 1, 2, 3, 4. And then finally, we have the endpoint. So it's kind of like this one. 4 to endpoint. Second coordinate to endpoint. Second coordinate. Okay. So this will still give us a score, right? To know how close we are to the cheese. Okay, and then we do a distance formula, we do a computation, and we'd like to minimize it. 5 steps, okay, before we reach the cheese, starting from our initial point, right? And then we return the distance. So this is a possible fitness function, assuming, okay, assuming that we didn't have any constraint. So think of it as a problem set wherein, or a problem wherein the rat is trying to reach the cheese without any obstructions. Okay, ito yung entry point natin. This is our rat with the tail. This is the cheese. Okay, so you have different solutions. Something like this. Okay, another solution, until you actually reach the cheese. So your population, now let's say population is equal to 100, your population will be 100 chromosomes that has this particular form. Now, since we identified earlier that it is a minimization problem because we want to get the shortest possible distance of the computed distances for each taken path to the cheese, no? Then we return the score, and then somewhere in our GA, we want to determine if it is less than a particular fitness value or less than the last ideal value, no, in this case. Right? Sige, questions first about this setup. Questions or clarifications? So again, the fitness function will return a score for a given solution. Whatever other thing that you pass to it be in aid of that fitness function. Right? And then you need to decide, are you maximizing it or are you actually minimizing that solution? Now, this is solvable by GA, right? Not necessarily pathfinding like Dijkstra's algorithm for fastest path possible, because you have to exhaustively go through all the possible paths. Here, we are approximating the best possible path using evolution. Okay. All right. Questions muna sa framing? Yeah. And that's what we have to develop, the skill of framing a problem and trying to develop a solution for it. Now, of course, it becomes complicated if we add constraints to our problem, such as roadblocks. No? You can think of it as having a roadblock that if I had a solution, this one, this one, this one, notice na tumatama tayo sa mga walls, no? This one, okay? What is the score for this solution? Yung tumatama tayo sa walls. What should be the score of that solution in order for it not to breed, so to speak? No?
Infinite or very large number.
Okay, we could flag it as an extremely large number para sure tayo na hindi siya sasama sa next iteration. So there's a likelihood that that solution will not be included as the ideal representative of our solution. Okay. Now it's the opposite. Kasi kanina, dun sa knapsack problem, if we hit the constraint, we set the score to 0. It's easy. No? Kasi gusto natin i-maximize your problem. But in the case of minimization problems, one thing we can do is we can set it to an extremely high number to force the system, to force nature to say na, oops, you're not ideal for the next generation. It's time to die or something like that, right? Okay, that sounds too morbid. So those are some things that you would think about. No? Now, we haven't discussed the mutation part yet. There is the crossover part that will allow you to breed ideal parents so that it comes up with a good solution that takes in characteristics of the other parents. Okay, but before we go to that, just to further exercise the way we solve for problems, this week, try to take a look at the what do you call this? at the links I've posted on YouTube. And let's just take one, no? This first one. Let's spend a few minutes to watch it. So this might take a bit of time to sort of try to think about, right? And this one is actually in 3D. So just for example's sake, let's assume that this is 2D space. Okay? Although it's nice because it's 3D, so you have nice visualization. And this is considered generative art. So if you're fond of art, you can try to create a genetic algorithm that represents something. Okay. So you have a picture of the Eiffel Tower. And let's go ahead and watch this. So this one reproduces not only Eiffel Tower, pwede rin si Homer Simpson. And at each iteration of the genetic algorithm, eventually it will come up with the ideal, wherein our ideal is the input image. Okay. Now to start thinking about this, an image is represented by a set of pixels. Now let's assume black and white image. No? Para sa sa Photoshop, no? We know that an image, each pixel has an intensity value of 0 until 255. Right? And this one is using GA with a bunch of sticks, okay, that tries to meet the ideal, which is a picture of the Eiffel Tower. Ayan, 3D siya, no? Pero again, just to keep our brains intact, no? Let's just assume that it is 2D. And the genetic algorithm is trying to find the ideal sort of visual for this image. Okay, so I think we have one more thing. Okay, you can even have some sort of real-time processing wherein the sticks inside the image will allow you to try to form the ideal image, which is the one that we find on the upper left-hand side of the screen. Okay. So now that you can see this, let's try to answer some fundamental questions. No? Is this a minimization problem or a maximization problem? Anyone? Is this a minimization problem or a maximization problem? Okay, if so, why? Again, yung hint ko is that a picture, a black and white picture, is simply a set of pixels that wherein each pixel has a value from 0 until 255. And the genetic algorithm is trying to get as close as possible to the ideal picture. So is it a minimization problem or a maximization problem? Anyone? Min or max? Are we trying to maximize something, or are we trying to minimize something?
I'd go for minimizer. Parang the closer it gets to the, I don't know how they graph the solution for it.
Yeah. Even if you don't know how to graph the solution, but you think it's a minimization problem. No, because you want to get as close to the image as possible. So that's correct. It's actually a minimization problem. You want to be as close. Yeah, it kind of looks okay. So there's an answer here sa chat. No? It's like the single perceptron algorithm, where it tries to find a set of solutions to be very close to the ideal solution. Okay, where the ideal solution is the image. Right. So the question is, how different is it from machine learning? Right. The GA is what we call an unopinionated algorithm, no, or a parameterless algorithm. Although it does have parameters, no, but the idea there is that it's it does not require other data to try to solve a particular objective. Unlike sa machine learning, remember the first algorithm that we tried to implement, yung single perceptron, wherein we had some simple form of regression or backpropagation, wherein it minimizes the value until some ideal, but it is based on multiple data points, right? This one, it does not require multiple data points. It just requires an objective, and it will try to reach that objective via the process of evolution. No, wala naman tayong, if this were a classification problem, similar to what machine learning classification problems do, which is the single perceptron algorithm, it tries to look for an ideal set of weights based on an existing data set. Now, it's supervised in that sense. Okay? It's trying to generalize it to classify a particular unknown data point. Dito, it doesn't care about the unknown data point. Okay, it's unopinionated. It doesn't have a specific way to generalize itself because it's only focused on a single objective, which is in this case the input image. Right? So it does share similarities in a sense na backpropagation sa ML or some other classification models, classification algorithms tries to minimize some error term. Genetic algorithm tries to minimize or maximize a particular objective. Okay. And usually that objective is just a single value. You can't apply machine learning here kasi wala ka namang multiple pictures of Eiffel Towers. If you had, then you can apply machine learning. So hopefully that answered the question. So in this case, no, we're not actually looking for weights. We are trying to minimize the distance between our solution, this one, with our ideal, which is the input. Okay. And there are different applications of this. Again, this is not machine learning kasi you are not trying to classify something. You are trying to optimize something. So it solves a different set of problems. That's one way you can also think about it. So this one is actually similar to our rat maze problem. We are minimizing the distance of something. Okay, we want to lower this distance value. Okay. And how do we lower that? Well, technically, our solution is a representation, or it will have the same dimensionality as our Eiffel Tower, the input image. So if this were a picture of 400 by, I don't know, 250, then all the pixels of a vector of 400 times 250 will be the value that we can probably use distance formula in to measure against the target picture. Okay. Now, this becomes complicated because if you notice, it makes use of lines. Okay, it makes use of lines to represent each area of the drawing. Right? But at the end of the day, the dimensionality of the picture will be compared to the ideal. You get a distance, that's your fitness function, and then it returns a score. Okay, that's why if you take a look at the video again, it's trying to mutate in such a way that it will move these lines. The constraints are actually that you have a fixed number of lines, of straws, if you will, no, in this particular art piece that will try to adjust its coordinates within the picture so that it can be as minimal as possible in terms of distance to the Eiffel Tower. Okay, so same goes for this one. Everything starts random, and then it will eventually evolve to the ideal space. So your constraint is something like you have a bunch of lines. So you need to figure out like the equation of the line. The vector of this isn't actually, it is the entire picture, but you have a fixed number of lines where each line can be measured by two coordinates. No? xy1, xy2, so that you can draw a line in between, which makes it art. So let's take a look at the second example. Okay. The second video. right? So here it's trying to match a painting, right? With a bunch of random shapes, circles, rectangles. No? But it's still GA. It's still GA in a sense that it's trying to match the colors of each. It probably has something like an alpha channel, no? That tries to match the colors of these shapes of each particular shape. That's why it's never perfect, because if it were pixel by pixel, eventually, after enough iterations, it will learn how to draw Super Mario in this case. If it's pixel by pixel, because if you had the same exact value of each pixel, then the distance will be equal to 0. The ideal solution is that the distance from the one of the solutions to the original image is equal to 0. We have other things here. Okay, so it's actually generative art in this case. Now, the reason why I'm sharing this is because it allows you to exercise how you would represent, no, the input or the solution, the chromosome that you'd like to compare to the fitness function. So if you were to implement it in code later on, although image processing is already rather a complex topic, no? But if you were to represent it in code, you know that the input of the fitness function is a solution, a matrix of pixels perhaps. Tapos meron ka ring picture, something like the ideal picture. So your function might look something like def image fitness function will be your solution plus the ideal picture or the input image. Okay? And then your score will be the distance between solution minus input image. It can be something like that. Then return score. Okay? Whatever that distance formula is for two values. And then you supply the constraints similar to what we did with the knapsack fitness function. Okay. Sige. Questions first about framing the problem of GA. Clarifications? Sige. So what I'll do is that on Wednesday, instead of having the problem set, no, because I think maraming mahirapan if we start the problem set immediately. I'll give more examples wherein your output should be an example of a fitness function. Just so again, we're trying to answer two questions. No? Every time we figure out the fitness function, we are trying to answer two questions. First, is it a minimization or a maximization problem? Second, what does the solution look like? And we know that the solution will always be in the form of an array. And the question is, the sort of the creativity part comes in, or the exercise part will be, what is the representation of each element of the array? What does a gene look like in the chromosome? Right? So we've given some examples here. Another thing that you could try to explore will be the mutation part, because the mutation does have an effect in terms of what is the probability that you will develop a new feature, a new characteristic for your chromosome to help the problem. Now, in our simple example, the mutation was, not the mutation, my mistake, the crossover, no? Which is, how do I, given two parents, no? How do I produce children, child 1 and child 2, that will share characteristics similar to the parent? Because remember, in GA, parents are ideal candidates that when bred together will produce more ideal candidates. So you want, and we know that something is ideal because we already figured out the fitness function. Okay? So the crossover does have a bearing in terms of how do we combine different characteristics of parents in order to come up with the best breed of offspring. Okay? Now, to explore that, one good way to exercise also is that I've included a paper Okay. One thing you could do to exercise your programming as well is to take a look at this paper called Crossover Types. This is a rather old paper already, back in 2017, which holds some of the more popular crossover types that given two parents produce an offspring or produce two offsprings. Okay, you don't have to read everything. You can go directly to the um, this one, section 4, which are the types of crossover operations. Okay, so it does give a visualization of how crossovers look like. For example, the one that we discussed last week is called the one-point crossover, wherein we randomly take a crossover point between two chromosomes and then simply get one half and the other half and then combine them to the offspring. Okay, that's simple. But there are more complex ones that has a better chance of producing a better sort of offspring. One such example is the two-point crossover. As the name suggests, you randomly select two crossover points, and then there's a specific way on how to adapt the different sections of parents to an offspring. Okay. So one way you could practice is to implement each crossover implementation, and you can validate your answer if it's correct because it does have a visualization of the crossover types. There's also this thing called order crossover, and there's also this thing called partially mapped crossover, as well as cycle crossover. Yeah, cycle crossover or CX. Okay. So two things for this week. We'll have more practice into how to frame a particular problem, okay, in terms of the fitness function and the solution. And then try to see if you can implement these crossover types. Okay. I'm still thinking about if we need to push for the submission this week, but for sure, we need to give sample problems that, with of course the implementation of the fitness function, in order to prepare us to try to answer those types of problems. Okay. Once we get a hang of it, then we can understand uh, the other the concept of NP completeness. No? Why do we need this randomness to understand NP complete problems? Okay. All right. Sige. Questions muna. Okay. So I won't keep you guys. Please watch out for a video this Wednesday. I was hesitant muna to upload last time because baka mamaya some of you are not still like comfortable with the setup of a GA. Okay, so again, the practice is when you think of a problem, answer the two questions first. Is it a minimization or a maximization problem? Second is how does the solution look like? Okay, and of course, the solution is in the form of an array. All right. All right. Questions? Okay. Now for the project, if you notice dun sa sign-up sheet, no, please do not fill in the the last column kasi that's for me to take down notes. Sa ibang after this, so those that were already approved, the next step is to answer the notes I've provided. Okay, so that will be the next step for at least for the project part. Okay, after that, then all that's left is the analysis in the paper, and then we're good for the project. Okay. All right, and that's it for today. Any questions first before we conclude? Clarifications? Okay, so for those about to go to the last checkpoint, again, I'll be expecting you answer dito sa notes natin. Right? Okay, so if there are no questions, that's it muna for today. Thank you for joining the synchronous session. And please keep, I'll email you once the videos are uploaded sa Canvas for the practice stuff for GA. Right? Okay. All right, baka gutom na kayo. So thank you again, and I'll see you guys next time. Thank you. Thank you, everyone. Stop recording now.
Thank you.